First, I'd like to say I really enjoyed sitting on the panel with everyone here. I thought you guys had a lot of great comments. So I hadn't had a chance to work with many of you before, but yeah, that was great. So appreciate the opportunity for doing that. So today, going to kind of give a whirlwind tour here, talk about some of the technologies and techniques in big data, and a lot of it based on our experience at Cerner. So I'm going to start off with a slide that probably no one expected here at a big data talk, and that is relational databases are awesome. And they actually are awesome. They do a lot of nice things for you. You may have heard ACID, atomic, consistent, isolated, and durable. They make it really easy to think about in that there's always a consistent state in the database. If I transfer money from account A to account B, these properties guarantee that the money is either in account A or account B and not in both and not in neither. These are great. They have great declarative queries, and they have a long track record of success. So really, I think that anyone that's looking to take this step into the world of big data should really, should also ask, will a relational model work for me? And actually should be asking, why shouldn't I be using a relational model? So use them. But you can't tell me you didn't see that slide coming. But all those advantages in a relational database model, it comes with a cost. So these great advantages, that's ACID properties, these globally consistent state, means global coordination across all these processes in a big database. And this type of coordination doesn't scale linearly. So if you kind of think back to the network effect, so you may have seen this diagram before. If you have two devices, there's one channel between the two. If there's 5, there's 10. And it actually grows as basically as an n squared as the number of devices. So basically, if I want to scale out, I need to add more and more nodes to the system. And if I really want strong consistency between every one of these nodes in the system, they all have to be coordinated in some way. So if I start with 2 nodes, great. 5 nodes, yeah, 10 channels, that's not too bad. Get up to 25, we're talking 300 channels, and it gets a lot worse from there. So the result is now it's true that the databases are optimized in lots of clever ways. Not every database node in the cluster is actively talking to every other database node in the cluster every time you do a transaction. But there's still this fundamental limit on scalability of a relational database. And so as a result, we need to look at, if we go beyond that limit, we need to look at other ways. So let's look at some ways that we can scale this. And we're going to look at how we can scale a number of different properties of the system. First, we're going to talk about how we can bulk process billions of records, how we can aggregate data and store data at that scale, how we can handle real-time processing of updates, and then finally, we want to be able to serve that data for online apps and analytics. Now, a lot of this talk is going to be centered around kind of the Hadoop universe, the Hadoop view of the world, but I think that we also want to look at this a little more generically in that a lot of the properties that make Hadoop scale are kind of the same properties that make really any scalable system scale. So we're going to start with Hadoop, but then we can expand from that. So let's look at bulk processing. So here's a little quiz for you. So which one of these is scalable? You can have a 1,000-node Hadoop cluster where all the jobs depend on some common process, or 1,000 Windows ME machines running independent Excel macros. So which one of these? Well, guess what? The 1,000 Windows ME machines is actually more scalable than a Hadoop cluster because we did something wrong. We built a job that depends on some sort of common bottleneck. You can scale anything as long as you can make it independent. So I think this is kind of the key. If you have systems where you can take a huge problem and process it in really independent chunks, you can make that problem parallelizable. You can throw more hardware at it and then scale with that growth. And if something's parallelizable, well, it's also scalable. So this kind of leads us to this shared nothing architecture. You may have heard this term. It's it's becoming a little bit of a buzzword, where shared nothing architectures are really greatly scalable because, well, they don't share anything between the states. But it turns out that most real-world problems, you have to share something. I can't just process a whole bunch of different things independently and never bring them together or coordinate or join them in some way. So usually, shared nothing architectures are great, but they're not sufficient to solve all the problems that we want to tackle. So this kind of leads us to, most of our designs have both a parallel part when we want to scale, and a serial part. So how can we think about attacking this problem? Oops. So the key is that we want to make the vast majority of our work independent and parallelizable, but still reason about the serial part. One way to reason about it, something called Amdahl's law, and you don't need to know the specifics of this. You can Google it later. There's a great Wikipedia page on it. But really it boils down to is it kind of tells us that imagine for any large-scale problem that we want to tackle, we can imagine if we divide that problem up into which portion of it can be executed in parallel and which portions of it are fundamentally serialized. And this will tell us how much we can speed up our problem because of that. So if you have a problem space in which I can only execute 50% of the problem in parallel, it doesn't matter how big of a Hadoop node I had or how many processes I throw at it. The most I can ever do is cut my processing time in half, because only 50% of my problem is parallelizable. This is kind of an interesting tool to keep in our chest. When looking about how I want to process a very large set of data, you have to understand the algorithms that we're using to process that data and understand what percentage of those algorithms can be parallelized. And Amdahl's law is kind of a convenient tool to do that. So given Amdahl's law, let's take a look at kind of the Swiss Army knife of massively parallel processing. That's MapReduce. So we're going to talk about what MapReduce is, how it works, and kind of expand that on. So really, it's really conceptually simple. You take your huge data set, you divide it up into many, many splits of data, then you run a function against each one of that, and a split just being a chunk, like a subset of data. You run a function against that, and then you combine the outputs, and that's the map phase, to convert that input, map it to some intermediate state, and then you take all those intermediate states and reduce them down into your final state to answer your question. So kind of the simplest example of MapReduce is, let's say I want to count all of the words in all of the books in the world. Well, doing this as a serial problem would take forever. I'd start with the first one book, do the next book, do the next book, take a long time. Very easy to implement in MapReduce. I basically divide, I can take each book, a set of each book, route it through a single mapper that counts those words. I output the number of words in each book, and then I basically just sum those in the reducer. So as a result, we have a very, very parallelized problem in that we can take these problem sets and run it against a massive MapReduce job. Of course, there's still a serial part of this problem. The output of the MapReduce have to be combined in the reduce phase and added up to get our final answer. But this is a much smaller space. The count of the words in a book is much smaller than the size of each book. So as a result, this can be handled very easily. We also have to note that the network is a shared resource when processing data. So even though I can throw a ton of parallel processors on it, if I have to send every piece of data that I want to process across the network, well, that becomes a bottleneck in itself. So this leads to an important step. Rather than moving data to the computation, we can kind of turn that, which is a traditional processing model, we can turn that on its head and really move the computation to the data. And so, the same picture before, but these blue boxes indicate a physical machine, where we actually move those map processing to where that actual data exists, so I don't have to send it all over the network when I want to reprocess it. And this is really kind of this is kind of like the basic unit of functionality for Hadoop. And of course, data, like I said, data locality is only guaranteed in the map phase. And the other interesting thing is some MapReduce jobs actually don't even need a reduce phase at all. So if you can do something that we don't have to route everything to a common reducer, you can eliminate that outright. So there's lots of options there. Now, here's probably the #1 way to shoot yourself in the foot when trying to do MapReduce jobs, and that is basically, imagine if we have every one of our processes depending on some external common process, and surely no one would do this, but it's amazing how often it happens. Imagine if we decided to write a server for some reason where we added the words together rather than doing it as a library in our map job. Well, suddenly we have our bottleneck. Suddenly Amdahl's law is working against us because everything is being serialized and to this point of contention of the service. So even if our word addition service was really scalable, we'd still have to scale it to the needs of the largest MapReduce job that will ever use it. And the result is that we really want to use embedded libraries over remote services. Again, we want to take that, we want to be able to move the computation to the data. And so this really kind of changes the way that we have to think about approaching these big data problems. I mean, so a lot of the techniques that I'm a fan of a lot of things. I'm a fan. Service-oriented architecture is great for a lot of problems, but if you want to process many petabytes of data, you're not going to send it all to a web service. You have to change the way we think about our designs and approach these problems. And of course, you can use those remote services for things like configuration, primer caches, just not for data element. So the next one, we talked about these kind of primitive MapReduce models, but counting words is great, but it doesn't really very useful. Most of us, don't get up and say, like, oh, I want to count all the words in the dictionary, count all the words in the world. So really, what we usually want to be able to do is take different kind of data sets, find some intersection, find some commonality, and bring them together. So basically, we want to join 1 billion records. So with some of these large data sets, this isn't something that you can do very easily in a relational model. But how do we do a join operation in MapReduce? And we'll just touch on a couple ways that we can do this. So first one is if you have one data set is very small, just copy it out to each one of your nodes that's processing your larger data set. But I think that the more interesting one is, I'll just skip to the example here. Oops. I think that perhaps the more interesting one is if you have a data set, say if you have persons in one data set, which could be many millions of persons, you have visits in another data set, you can actually do a join in a MapReduce job where you route a set of your persons to one set of mappers, you route your set of visits to another set of mappers, you group by some person ID, and then you basically send the related items to the same reducer. So these are kind of like this is like the primitives, these are like the building blocks of dealing with big data. And I talked a lot about Hadoop, and I talked a lot about MapReduce, but I mean, these kind of same patterns still apply. Moving the computation of the data, identifying subsets near that data, and only streaming those very limited subsets of data to what you need to process downstream. And so given that those are primitives, there are, of course, a lot of higher level constructs. So we talk about just in the Hadoop world, there's things like Hive, which is kind of an SQL-like language over Hadoop, or Pig, which is a more procedural style language. There's better APIs like cascading and crunch. So I think it's really important to understand these primitives, but I don't think you want to spend your days writing these low-level MapReduce jobs. Use a higher-level construct. And kind of to that higher-level construct point, I think one of the things that came up in the conversation was MPP databases. And so you kind of see this, depending on the community you're talking to, you might see this kind of, maybe not conflicts of two word, but there's some tension between Hadoop MapReduce community and MPP database users. And I think that it's important to kind of call this out and what these two things do differently. So in MapReduce, we have a distributed file system, whereas MPP is a relational model. And MapReduce is more geared to unstructured or semi-structured data, often just raw data. MPP is more of a structured relational model. You tend to use DSLs or just Java versus SQL. I mean, so and MapReduce doesn't do a very good job of iterative operations. We can talk a little bit more about that. MPP databases do a much better job of highly iterative queries that run against the data because it can keep related data sets in memory for multiple iterations. Now, MapReduce allows us to basically run arbitrarily complex programs next to data. One of the things that we do at Cerner is we actually have a natural language processing engine in which we take healthcare documents and we run this natural language processing engine on the physical nodes to do analysis of all these healthcare documents. And this engine is actually very big, very expensive, takes a few gigabytes of RAM to run. It's not something that you can run in a user-defined function. But if you don't have something that upstream, an SQL user-defined function running next to the data is probably maybe a better fit for you. And finally, MPP is going to have good or better interactive query support. The point of all this is that things like MapReduce and things like MPP databases are really complementary. And we're going to talk about some other technologies as well. There isn't, I think Scott made up the point, is that a lot of people think Hadoop is big data, and he's absolutely right. Hadoop is not big data. Hadoop is one tool out of many tools. It just happens to have more visibility because, it was modeled after a lot of what Google did. And the pattern that we're kind of seeing is that MapReduce is great to take raw data, to normalize, to clean it, to reconcile, to codify that data, to create some structure around it, and then we can load it into an MPP system or some other system that's more geared towards interactive, more human use, and we'll have some more examples of these later. So before we get back to that, I'm going to touch on, we talked about kind of techniques for processing many millions of records. Let's talk about data aggregation and storage of these records. So let's talk about, just briefly, in the Hadoop file system. Basically, Hadoop will scale to very many petabytes, and it does that again, taking a huge data set, splitting them up into different ones that can be scaled independently. There's a name node that just keeps track of where they are, and everything is written in triplicate. So if you lose any node or any two nodes, you don't have any chance of losing your actual data in the system. And this is pretty common pattern. So here, a client application that needs to write data, it'll look up where it needs to write it from what's called a name node, it'll write it to a data node, and it gets replicated across a couple of places. Again, just this simple peer replication, commodity hardware. It doesn't offer a lot of the nice consistencies and global views of state like you would in a relational model, but it scales really well. Similarly with reads, you just go out and look up where the data you want, you load it from your data node. So of course, HDFS is great, but again, all these technologies are trade-offs. They have shortcomings. HDFS, there's no random reads and there's no random writes. You can seek to a file and you can append to a file, but you can't randomly access records from a file. So we have to balance these trade-offs and use the right tool where appropriate. So at Cerner, one of the tools that we've been using on top of Hadoop is we're actually pretty extensive users of HBase. And HBase, the tagline, if you look at the HBase book, is real-time, random access to your planet-sized data. And that's really what it is. HBase is simply a random access layer on top of your Hadoop infrastructure. It kind of simulates random reads and random writes while taking advantage of Hadoop's locality of data. It exposes data as tables split across many regions, hosted by many region servers. Again, the same pattern of taking data on commodity hardware and spreading it out. And it preserves scala, data locality, and the MapReduce features of Hadoop. And this is kind of, I think this last one is kind of the value of an HBase. Frankly, there's a lot of solutions that are a lot easier to use, set up, access, manipulate than our HBase. So if you want to look at a React or a MongoDB, there's a much lower barrier to entry than HBase. Really what HBase does is it allows you to have random access on top of a Hadoop ecosystem. And if you need Hadoop, it's a great tool. If you don't need Hadoop, then I'd strongly encourage looking at some of the other options. So we like to use HBase when we have noisy data, when we want to apply massively parallel processing to handle these huge write loads. HBase absorbs write loads very well as a scalable key value store. And of course, but again, drawbacks. It's the great tool for many jobs, but not for every job. And so ultimately, we need to use, the data needs to align with the needs of the application. And so we're kind of seeing a pattern that's emerging from all this that we're talking about. So you might have Millennium come in, and this is kind of our Millennium is Cerner's largest system with regards to how we run healthcare across the country. So we have a variety of sources coming into the system. We can aggregate it in Hadoop. We can process it with Hadoop and HBase. But then the output of that is just kind of fits the need of the application. But one thing to keep in mind is that we have a potential bottleneck here. So if I have billions of records stored in my Hadoop cluster, but I want to move a subset of that into a relational database or an MPP system, I can't just do individual inserts updating those records one at a time. So what's kind of emerging is these connectors for Hadoops. So rather than doing direct inserts, I basically can run a MapReduce job that generates the internal Oracle files. There's the Oracle loader for Hadoop, or do bulk loads for MPP systems. Most of these technologies have a way where I can construct the subset of data that I'm interested in, compute that up front, and do a bulk load into my target system. So this is great because I do most of my computation in the Hadoop cluster, but I can transfer that subset of the data to the MPP system where our data scientists are able to go and interact with that more directly, since that's the right tool for many of their jobs that they're tackling. And finally, I'm going to, one of the things, so we kind of have this pattern, I think you can kind of see this Hadoop ecosystem, this aggregation of the raw data, cleaning up, processing, using MapReduce, using it as kind of, you kind of think of it as a big ETL system into these other ones. But we're actually missing an important piece here. And so, in that everything that we've done is very batch-oriented. Hadoop MapReduce is very batch-oriented. And sometimes we need to complement that with real-time processing as well. So this kind of gets to a model that actually the creator, Scott mentioned Storm, and actually the author of Storm actually came up with this model of thinking about it. What if Hadoop is great as our batch layer, but we really need a speed layer because MapReduce isn't going to handle these real-time incremental updates in the system. And the speed layer has a lot of different properties that kind of complement this batch layer that we're talking about. So in Hadoop is great for dealing with many years of data, many billions of records. We move computation to the data because the data is too big to move, it. It supports bulk loads. But it's not very good at this, what we call the speed layer which deals with minutes or hours or at most days of data. We move the data to the computation because it's streaming into the system. It's much more efficient to move that than to move our computation around. It's low latency, and we can process it in seconds as it enters the system. And so this is kind of an approach that's starting to emerge of complementing our big data, our Hadoop systems, with data that's kind of flowing into the system, the speed layer, these incremental updates. And so some technologies that can do that is we're actually fairly significant users growing users of Twitter Storm, which is an open source real-time processing project. Scott mentioned it. There's a lot of alternatives as well. S4, there's complex event processing engines. Different one of these may be the right tool for your job. And then I've kind of drawn Apache HBase kind of right in the middle there because HBase, since it kind of is that bridge between Hadoop and real-time processing systems, I can do random access and updates in Hadoop but still have data locality for my large-scale MapReduce processing. So it kind of is that connector for us between the batch layer and the speed layer. And of course, there's other ways that we can do that as well. So now I think I'm going to close with just a challenge that I'd like to mention for everyone. And that is try and design your system so you can process the world's data overnight. And by this I mean, we talked about it on the panel, and somebody asked the question of whether you clean data at the edge or whether you clean data after it enters the system. And I think a number of people said, after, just get the data in there and then we can do it afterwards. And part of the reason for that is that what we can do once we have all that data in the system is that as we find new ways to process it, to analyze it, to clean it, we can deploy that. We can deploy these massively parallel computations to that system. We can rebuild our downstream data models, and we can do it nightly. And this is, I think, one of the things that is really exciting about these new opportunities in the space of big data. So where previously the center of the universe was a data warehouse, a data mart, which was really big, expensive, took forever to update and to maintain. But now, using the techniques that are starting to become available, we can keep all of the raw data, all that raw source data in its raw source form, and we can rebuild our data models overnight. So as we identify, I wish my data model had this, or I wish I could query the data like that, or represent it like this, we can recreate that. And so I think that what we're seeing that's exciting is this tightening pace of innovation. So rather than having to be a very long cycle to make a modification to my data model, I can rebuild stuff, I can create custom data models. It's almost getting to the point where what was a big expensive data model is becoming maybe discardable isn't the right term, but we're headed in that direction. So we're seeing this kind of quickening pace of innovation, and it's pretty exciting to be riding that wave. So those are some of the advantages of that. And so with that, I'll open it up and ask if anybody has any questions. Yeah, so the question is, do we use middleware for when we're queuing up stuff for the relational piece? So there's a couple pieces there. So one, when we actually bring in data from the source system, we actually have our own Java processes that will scan that and bring that into Hadoop. There are a number of open source tools that do that for you. Scoop is a great example. We had very low latency needs, so Scoop didn't quite align with what we need. But if you don't have very low latency, as in second type latency, I'd recommend using something like Scoop to basically bring data into Hadoop and to transfer data into a relational database. Similarly, Oracle's data connector offerings work as well. For a thing that we wanted, if we want stream-based processing, Twitter Storm is kind of growing to be increasingly, our choice there. And can talk. I mean, there's a lot of options there. We chose Storm kind of as the middleware in that space because it had really good message processing guarantees. So if somebody's curious about Storm, I'd be happy to talk about that in more depth. Yes. Yeah. Mm-hmm. Yeah. Yeah. Right. Yeah. Okay, great. So, sure. So, in case everybody, in case not everybody could hear, the question is, what kind of business problems are we trying to tackle with this? And there's really a couple. One, that kind of our initial steps into big data was actually creating a search for the medical record. Basically, a huge amount of medical data is stored in textual documents. And it just simply wasn't, and search engines are big, complicated, hard to deploy, and it simply wasn't efficient to kind of deploy that, in terms of each medical record installation. So basically, the first business problem that we tackle with that is being able to do natural language processing and build search indexes for medical records. Now that was kind of the first step, and we've grown into a number of other things. We have, currently right now, we're bringing data together from a variety of EMRs in order to do things like detect actually health risks. So a good example, if somebody's at risk of sepsis, we'll run this through an algorithm to determine, basically based on a number of vital signs, labs, measurements, if this person may actually is potentially septic, and then actually fire off alert of that. Beyond that, our latest thing that we kind of did a soft launch, we basically have an iPad application to explore healthcare data in a way that we weren't able to explore it before. One of the things that we had a challenge is that when you have a large database, the data is not always structured in such a way that a user may want to explore it. So we're actually bringing data into Hadoop, processing it, and creating these new data models in the cloud. The cloud's kind of an overloaded term, but basically in our data centers, so that somebody can explore that data more quickly and more efficiently than they could, against their original database. And then finally, ultimately, I think we have much bigger visions beyond that. Things like being able to understand, look at large populations of people, identify, people that have enrolled in this, identify certain health risks and be able to help manage those health. So I think that there's those people's health. So there's really a wide variety of things. We have a number of paths that we're leveraging this big data direction.
Does anybody else have a question?
So it's a pretty common problem that you'll have a document of some sort, and then you'll have a bunch of metadata about a document, and then you'll have a bunch of events that occur on this document. Now, you can either look at solving this from the two extremes of fact dimensional and writing it all out to a single data entry. Which way do you lean more towards when you're doing big data analysis?
Yeah, great question. So basically, I think that we're finding increasingly is that while while a lot of problems may have commonality in terms of the data model that they need to solve the problem, there's a lot less commonality between them than you might think. So a great example is if you want to identify, somebody that's interested in something as simple as respiratory rate, if in just a clinical setting, it's a very simple concept. But if somebody's interested in respiratory rate that's trended over years of time to a very specific thing, even such a simple concept can have very different representations and very different data needs. So I think that ultimately it's more important with big data is to start with the question that you want to answer and then figure out how to represent that data in order to help you answer that type of question versus let's see if we can figure out what our big data model is and then try and align that with the question. So I think when determining how to structure it, start with the question you want to answer, figure out how to represent like that. And frankly, I'm not the expert in star schemas and representing these data mining type data structures, but that's kind of the direction that we're going. I feel like that I want to enable our data scientists in order to create these new data models in order so they can meet their needs. But I hope that they feel like they have the flexibility to model the data in whatever way is appropriate for the problem at hand. So, thanks.
Anybody else? All right, I think we're close to 4 o'clock here, so thanks Ryan.
Right.
Appreciate it.